section 9.3, extra example number 10, is the express lane faster? That's what we're trying to figure out here. This is paired data, so it's still, you're still taking a sample on one population, but you're reading two different values. One's the express lane and one's the regular lane, and you're taking the difference. So it's still a one sample test. In the next chapter we'll get into two sample tests when we have two distinctly different populations that we're comparing. So here it's particularly important that you define mu, and mu is going to be the difference. So we're going to say mu sub d for difference is, and we really have to define it here, is the true mean difference. And we have to define which direction we're going to subtract in. Otherwise, that we won't be able to interpret our answer. So we're gonna go in the direction of the regular lane minus the express lane. And what do we hope our difference is? Positive or negative? Positive, right? If we do think about it. If we do regular minus express, we want express to be faster, so it takes less time. So regular minus express should be positive. So the true mean difference, regular minus express in time. So what's H sub naught? So remember it's the statement of equality. It's still going to be equal, and it's always going to be 0 when we do the paired. When we subtract, if they're the same, the difference is 0, right? So when we do paired test, it's always going to be 0, and then the alternative is that the difference is greater than 0. That's right. Right. Okay. So so we are going to do a paired. This is the name of the test. Paired one sample. Is it T or Z? T-test. T-test. One sample T-test. Okay. If our three conditions are met, so number one, data comes from a random sample. Data from a random sample. 2, now here, remember this please, do we need to check the normal condition on this and the differences? We're only interested in the differences, okay? So you only need to check the normal condition on these numbers. So we'll type those in and look at it on a box plot. If we do that, you'll see it's only going to be slightly skewed right. So let me write it like this. The differences are slightly skewed right. I'll type it in a second. Slightly skewed right, no outliers. So even though we have less than 30 data values, we should be okay. And I'll type that in just a second. And then the independent condition, they're just differences. There's an infinite number of differences possible. That's all you would say for that. There are an infinite number of differences. So let's type those in so we can get the mean and the standard deviation. So second plus 712, clear that. So we're going to type in these differences in edit L1. So we have 5, 2, 4, 6, negative 46, 121, 30, 55, 79, negative 94, negative 17. You're doing this too, right? 95, 20, 14, 129, 9, 42. And then you do, turn this on, go to the one with outliers, graph. Oh, that doesn't look very good. So zoom, 9, and that looks much better. So it's just skewed right, slightly skewed right, no outliers. On a test, you have to draw that. So let's draw it. So we would draw that here. Draw that. Okay, so now we're gonna do, we can do stat 1var stats, calculate on L1 to get the mean and standard deviation. So x bar is 42.7 seconds. S sub x is 84.0 seconds. Test statistic t equals 42.7 minus what? 0, right? That's what was stated in our null hypothesis. That means that they would be the same. But the difference is actually the sample mean is 42.7 seconds over 84 over the square root of 15. So if you very carefully type that in, it's about 2 standard deviations above the mean. So we're going to find the probability that t is greater than 1.97 is equal to TCDF. Our lower bound is 1.97, upper bound infinity. Degrees of freedom is n minus 1, and you should get 0.034, so there's a 3% chance of that happening. So you would say, since p-value is less than alpha, we reject h dot. And what does that mean? So what does that mean? Yeah, there is convincing evidence the express lane is fast.